Good morning to all of you. My name is Dr. D. Venkateswarlu, presently working as Professor and HOD of Civil Engineering Department, Godavari Institute of Engineering and Technology, Rajamahendrava. Today, I am going to discuss about statically determinate and indeterminate beams. It comes under structural analysis. Structural analysis. As a civil engineer, in our previous semesters, we have studied about strength of materials. There we have seen simple stresses and strains, shear force and bending moment diagrams, deflection of beams, thin and thick cylinders. And in continuation to that strength of materials, we have discussed about the mechanics of materials also. There we have studied about principal stresses and strains, torsion of shafts, columns, analysis of columns, analysis of pin jointed frames, etc., etc. They are all comes under statically determinate beams. As far as this structural analysis is considered, here we have to analyze the indeterminate beams or structures. The structures are broadly classified according to one classification. They are classified as statically determinate beams and indeterminate beams. Now let us see what is a statically determinate beam and what is a statically indeterminate beam. What is a statically determinate beam and what is a statically indeterminate beam? Now, you just see here some of the examples of statically determinate and indeterminate beams. For example, if you see the cantilever beams, they are statically determinate. Similarly, simply supported beams, overhanging beams. If you see statically indeterminate beams, propped cantilever beams, fixed beams, continuous beams, these are the statically indeterminate beams. Here, we can see the different types of determinate and indeterminate beams. Here, in the picture, we can see a simply supported beam. This is a statically determinate beam. Similarly, a overhanging beam, a cantilever beam. These are all comes under statically determinate beams. Now, let us see what are the various types of statically indeterminate beams. A continuous beam, propped cantilever beam, and fixed beam. These are treated as statically indeterminate beams. Why they are treated as statically determinate and why these are treated as statically indeterminate beams? Based on the degree of static indeterminacy, we can decide whether the given beam is a statically determinate or indeterminate. If you see the definition of this degree of static indeterminacy, the degree of static indeterminacy is the number of redundant forces in the structure. Therefore, the degree of static indeterminacy represents the difference between the number of static unknowns, which includes reactions, internal forces, and the number of static equilibrium equations. As we all know that the simple equilibrium equations available are three numbers. One is total horizontal forces are 0, total vertical forces is equal to 0, total moments in a given element or a part of the structure or a structure is equal to 0. Those three are known as the simple static equilibrium equations. For a general system of loading, a fixed beam is a statically indeterminate to third degree. Why it is third degree? That also we will see in our next slides. For vertical loading, a fixed beam is a statically indeterminate to second degree. Now you just see how to calculate this degree of static indeterminacy. For example, propped cantilever beams. The degree of static indeterminacy of this propped cantilever beam is, in this case, the number of unknowns are vertical reaction and a moment at fixed support and a prop reaction. Therefore, the total number of unknown reactions are 3. By eliminating the horizontal reaction. Therefore, out of these 3 simple equilibrium equations, if you remove horizontal reaction, then the number of equations available are 2. Therefore, 3 minus 2 is equal to 1. Therefore, the degree of static indeterminacy of a propped cantilever beam is equal to 1. Similarly, for a fixed beam also, at fixed support, the number of unknowns are 3. One is vertical reaction, horizontal reaction, and a moment is also there. Therefore, by omitting the horizontal reactions, therefore, the total number of unknowns at both the fixed supports are 2 plus 2, 4. 4 minus 2 is equal to 2. Therefore, the degree of static indeterminacy of a fixed beam is equal to 2. Now, we see how to analyze the fixed beams. As we know that the degree of static indeterminacy of a fixed beam is equal to 2. Therefore, the number of equilibrium equations available are 2. Therefore, we have to generate some additional equations to analyze the fixed beam completely. Let us consider a fixed beam and is subjected to loads W1 and W2 as shown in figure. Let VA and VB are the reactions, vertical reactions at A and B. Let MA and MB are the moments, fixed end moments at A and B. These beams may be analyzed in the following stages. Let us first consider the beam as a simply supported beam with external loads. For this beam, let it be case 1. For this beam, let us draw the bending moment diagram for this case. Then in the second stage, what we have to do is, let us consider only the fixed end moments MA and MB. For this loaded beam also, we have to draw the bending moment diagram. This is known as the fixed end moment bending moment diagram. By combining stage 1 and stage 2 diagrams, we can draw the final bending moment diagram when a fixed beam is subjected to external loads W1 and W2 as shown in the figure. Now, what we have to do is, we have to develop some compatibility equations. Here you can see the stage 1 diagram. This is the stage 1 bending moment diagram. This is purely because of external loads only. The stage 2 diagram, that is fixed bending moment diagram. This diagram is because of fixed end moments at A and B due to fixing of the supports. By combining these two, we can develop the resultant bending moment diagram. Now, how to develop the equations which requires for the complete analysis of fixed end beams, fixed beams. We know that elastic line equation is given by EI d square y by dx square. Let us consider a section which is at a distance of x from end A. Therefore, the bending moment at that section is equal to mx minus m dash x. By integrating the above equations and by substituting the appropriate boundary conditions, we can generate this equation. A is equal to A dash, where A is the area of the bending moment diagram due to external loads only. A dash is the area of the bending moment diagram due to fixed end moments. This is the one equation which requires to analyze the fixed beams. Similarly, Again, consider the elastic line equation EI d square y by dx square. At a distance of x from end A, mx minus m dash x, that is the net bending moment at the section under consideration. Now let us multiply this equation with x on both sides by again integrating this equation, and by substituting the appropriate boundary conditions, we can develop another equation, x is equal to x dash, where x is the distance of the centroid of the free bending moment diagram from A, and x dash is the distance of the centroid of the fixed bending moment diagram from end A. By using these two equations, one is A is equal to A dash and another one is x is equal to x dash, we can therefore the number of equations, available equations are 4. Sigma h is equal to, sigma v is equal to 0, sigma m is equal to 0, and A is equal to A dash, x is equal to x dash. By using these 4 equations, we can completely analyze the fixed beam. These are known as the compatibility equations. A is equal to A dash, x is equal to x dash. Finally, we can completely analyze the fixed beams by using this method.